Alrighty, let's go ahead and get started. So I was looking at the calendar, the academic calendar, to see how many classes we have left, when are the final exams, things like that. And it looks like we have today and then next week, and then the week after next, we'll have one day and then exams start. Um, so the plan for the rest of the semester, the way I'm going to do it is we're going to start into the final big overarching topic, which is going to be optics, light and optics. And so we'll work on that today and next week. And then the following week, our last day, we'll do the final exam review. So what that means is we won't have a third exam, just because if we had a third exam, that's at least one last class, if not two, one less class, because we need a class for the test and we need a class for a test review. So instead, we'll work on the material and then we'll just have the material on the final exam with everything else. That way we can look over this topic, which is, as I said, the point of this semester is to kind of get a nice general overview of the things you'll be seeing when you get to general physics and beyond. So you'll be better prepared to take those courses. And so I think it'll be better off for everybody to at least look at it. We won't be able to get through the whole topic. We won't be able to get to like lenses and mirrors and things, but we'll be able to do some of the important stuff at the beginning. And so that's what we're going to do this week and next week. Then we'll have the final exam review the following week, and then that's when the final exam schedule takes over. I don't have the date for the final exam on me right now. I know it's been sent by email, so if you are curious about the schedule for final exams, what day or what classes and things like that, I guess probably our next class I'll have it with me and we can discuss when ours will be. But for your own, information, I think the registrar has sent it already a number of days ago, so you can look in your email and it shows based on what time the class period is on what day when the final exams will be. So that's kind of the plan for this the rest of this semester. Start into optics, discuss the topic as best we can, get as far as we can. We're not going to be able to finish it, so I'm not going to rush through it or anything, but we're going to get to what we can get to. And then our last day will be the final exam review, and in the final exam we'll have optics as part of it. So with that said, let's go ahead and start into the discussion of light and optics. Now, in order to discuss light, of course, we have to understand what light actually is, because we have our everyday concept of light. You obviously know when a room is light or dark. You go outside in the daytime, it's bright outside, there's a lot of light coming from the sun. You go at night and it's a lot darker. We understand that at a very easy conceptual level, but what actually is light? There was a big debate forever about what light is composed of, and the biggest names in all of physics debated about this. For instance, Isaac Newton, probably the father of physics or grandfather of physics, however you want to say it, back in the 1600s said light was a particle. He thought that when light is shining on an object, what's actually happening is particles that we call light are coming from the light bulb, or in his case, the candles or the sun or whatever the case is, whatever's creating the light. Particles are coming from that object and they bounce off. That's what reflections are, or they get absorbed into the material or whatever. And you have different colors and all that kind of stuff. But then people didn't really believe it, because a lot of the physical characteristics of how light actually worked were more wave-like properties. You had things like interference. If you have two, let's say two beams of light coming from the same source or something like that, they can interfere with each other. And interference, that is to say, if you have, light coming here, and when they combine together, you get kind of dark and light patterns. They cancel out or they add to each other. That type of characteristic doesn't happen with particles. Particles, if two particles run into each other, they bounce off, they reflect, they hit each other. But interference is purely a wave phenomenon. Water waves, if you have a pond and you start tapping the pond in one location, waves get sent out. But then if you tap in another location at the same time, then you have, two waves coming in and they combine together, and you'll have parts of the water where it should be waving up and down, oscillating up and down, but isn't. It's actually staying completely flat, and that's because the waves interfere with each other and create nothing. But then there are other parts where the waves are twice as big as you think they should be because the waves added together. Well, that happens with light as well, and it happens with sound too. And so most scientists at the time thought light is actually waves. And that's what most of the physics of light was based on. Maxwell in the 1800s, who is the physicist who basically did all the mathematics behind how light works, said, nope, light is absolutely a wave. It's not a particle. Newton was wrong. I'm sorry to say. He was a smart guy, but he didn't know everything. And so he developed the whole theory of light as a wave. And then out comes Albert Einstein in the 1900s, and he says, oh, there's a problem. There's a problem because there's this effect where if I shine some bright light on a metal object and I study it closely, electrons get shot off from the metal object, from the surface of the metal. And that doesn't make sense. If this is a wave, certainly a wave isn't going to do that. But if I have particles and I throw a bunch of particles at a metal object, then it can knock pieces of the metal off. So this effect seems to show that light acts kind of like a particle. And so what wound up happening was physicists found that the way light actually works depends on how it is you're trying to test it. If you're trying to see it work like a wave, you're trying to look at its wave-like properties, then it acts like a wave. But then if you do an experiment to show its particle characteristics, it acts like a particle. And where this really gets deep and very, very interesting, because it doesn't work anywhere near what you think it should work like, is in quantum mechanics. Quantum mechanics tries to explain, it's one of the things it does, is try to explain the nature of light. And it turns out that what we believe now, the current understanding, which explains every experiment we've seen, we haven't seen any experiment that goes against this theory, but that doesn't mean the theory is right, because it certainly seems like it's incomplete, is that light is neither, or light is both. That is to say, the problem we're having when we try to describe what light is it a wave or is it a particle, is the fact that we're trying to define it based on things we know. And what we know is a thing can be a wave or a thing can be a particle. It's two separate things with completely different physical characteristics. And that's all there is to it. That's all there is in a universe. There are waves and there are particles. And that's the issue. The issue is our own ignorance trying to describe something. And the only thing we can do when we want to define or describe something we don't really know too well, is we must inevitably describe it based on other things we do know well. Because why would I define something using a bunch of words nobody knows? Because now I just need to define those words. So we have to define things based on other more simple things, or at least other things we already know about. And all we know about are waves and particles. But it seems that actually this is some third thing. It's neither a particle, nor is it a wave. It is something, we don't have a name for it. It's this thing. And the way this thing happens to work is it happens to have characteristics of both particles and waves. Now, what we say is it's a wave-particle duality. That is, light is kind of both a particle and a wave at the same time. Quantum mechanics defines this much more clearly. It's still a bit hand wavy at first, the philosophy of it. And that's the biggest issue most people have with quantum mechanics is the theory is great. It is the most accurate theory ever invented by man. It's more accurate than any scientific theory you can think of, more accurate than Newton's laws of motion, more accurate than anything in the world. We can set up an experiment, use quantum mechanical theory to predict what's going to happen, and we'll get the right answer. The issue is the answers we tend to get are not deterministic. That is to say, they're probabilistic. The best I can possibly do is say, well, I set up this experiment, and the point of the experiment is to say, if I have an electron and I put it in this location under these circumstances, what's going to happen in 5 minutes? Where is the electron going to be? Well, if this were Isaac Newton, then I'd be able to perfectly tell you, I know exactly where it's going to be because I see what are all the forces. So I do my little F equals ma on the particle. And I know that after a period of time, this particle is going to move, it's going to have this acceleration. And so after 5 minutes, it's going to be over here. Quantum mechanics says that's not true anymore when you get to the quantum level. Rather, what I can say is there's a 25% chance it'll be here. There's a 40% chance it's going to be here. And there's a 35% chance it'll be there. Now, I can't tell you which it'll be when you actually measure it, but what I can tell you is if you measure it 1 billion times, 25% you'll get this answer, 40% you'll get this answer, and so forth. And on top of that, quantum mechanics doesn't tell you why. It doesn't tell you how things happen. For instance, this is a bit of a tangent on quantum mechanics, but there's a famous, particle in a box. You have you can think of it as a box whose walls are extremely high, and you put a ball in the box. And you say, okay, the ball is just sitting there. It's got a certain energy, a certain gravitational potential energy, certain kinetic energy. It may be moving, maybe it's bouncing off the walls and stuff. But there's no way the ball can possibly get out of the box, because in order to do that, you'd have to feed the ball enough energy to lift it above the wall. Or you have to feed it enough kinetic energy to break the wall, something like that. But this ball doesn't have that energy. We know it doesn't have the energy, and we know that there's nothing in the system that can give it the energy. So Isaac Newton would say, well, obviously the ball is going to be in a box. It's going to sit there forever, and there's nothing you can do about it. Quantum mechanics says, no, this isn't true anymore. If instead of this being a ball, this is an electron or a proton, then I can wait 15 minutes, and all of a sudden the ball's over here, completely out of the box. And it's true. It happens. It happens all the time. In fact, most of the electronics we have depend on this being true. Almost everything depends on this being true. Our TVs, our microwave ovens, everything. This happens. An electron placed in a system it cannot get out of basically teleports out of the system. And quantum mechanics tells you it's going to happen. It does happen. Quantum mechanics tells you with what probability, how long should you wait for it to happen? And these answers are perfectly good. What it doesn't tell you is how it happens. We can't track what happens to this electron. We can't say, oh, I know what happened. A piece of heat came in and gave the electron a little extra energy. Or I can't follow the electron. I can't see it actually move over the wall and come to the other side. All I know is that it was here at one moment of time, and then at another moment of time, it's over here. And we can't even say that it actually moved through the space between them. We have absolutely no idea how it got there. This is the issue with quantum mechanics, or one of the issues. It is a very accurate theory that predicts to the best of our abilities what can happen. What it doesn't tell us is how anything happens or why they happen that way. We just accept that this is what happens. I can try to, come up with excuses, but the theory doesn't tell me. Newton's laws of motion, you see a car, the car is moving at 35 miles per hour, and then all of a sudden, sometime later, it stopped at a red light. Well, you know exactly how that happens. The person steps on the brakes create friction on the wheels and slows the car down to a stop. Heat is produced. We know all the little bitty pieces of the system that make the fact that the car moves from one location to the other and stop. Here, quantum mechanics says this is going to happen, but we have absolutely no idea how it happens. All we know is that it does. And so that theory is trying to explain light for us, and it explains us very well, but we're left with things like this wave-particle duality business where we can't say light is this word. Like we say it's a particle. Well, we've defined it by a word we know. We don't have a word to define what light is. So we try to define it with other things we know, and that is particles and waves, and we say light is both. All right, well, after a while, you just kind of get used to that fact. You know that it's got both of these properties, and so depending on the circumstance, it'll act as a particle. That is, it'll bump other particles, it'll reflect off in certain ways, it'll knock particles off of another material. And then at other times, it acts as a wave. It interferes with itself. It interferes with other light waves and things like this. So the first thing we need to know is light, both particle and wave properties. Now, what we're going to do for our purposes at this level of physics, it's easiest and actually most informative to talk about the wave properties of the light. The particle properties are more advanced. You get to that when we start talking about quantum mechanics and things. The wave properties of light is what we see most of the time in our everyday life. And so that's what we're going to start with. If light is a wave, what is the thing waving? That's a question. For instance, we say water waves, we know exactly what's happening. There's the water is the medium, and somehow pressure was exerted on the water in some way, whether it's the wind pushing it or the moon's gravitational pull on the earth or whatever. A pressure, a force was pushed onto the water, which pushes down the particles in one location, but water is an incompressible fluid. And so if it's pushed down, another part must be pushed up. And so you get this wave, and the wave travels through the water. So for a water wave, the water is the thing that waves, obviously. Or we have a string, a guitar string, for instance. Guitar string is fixed at the two ends of the string, and you pluck it. You flick it in the middle, and the thing vibrates. And so there's a wave that forms in the string. What is vibrating? What is waving? The string's material. The particles in the string move up and down, and that up and down motion travels throughout the spring, back and forth, reflecting back and forth. Sound is another wave. The way sound works, your vocal cords vibrate. That applies pressure to the air molecules surrounding you. And the air molecules move back and forth because of this pressure in the direction of motion towards the person you're speaking to. And so when it comes to sound, the thing that is waving, quote unquote, is the air molecules. They're moving back and forth because of the pressure you exert. So what is light? If light is a wave, or it has wave properties, then what is the thing that's waving for light? Well, first thing we know about it is it's actually a set of two different things at the same time. Another word for, or another term we use for light, the more scientific term, is what's called electromagnetic radiation. That is the official scientific term for light. Electromagnetic radiation. So radiation, obviously, that just means something coming from another object. It radiates from the object. It's sent away from this body or from a source. What is the thing that's sent away? An electromagnetic wave. Obviously, electromagnetic tells you exactly what is going on. There's an electric field and a magnetic field. Now, when we get into electricity and magnetism in general physics and beyond, we learn a lot more about these fields. But for now, what I can say is, number one, electricity and magnetism, while they seem to be two different things, there are electric charges out there, so things can be charged. You have electricity, you have a current, amps, watts, all that stuff, circuits. And then there's magnets. You've got North and South Pole. You got the poles of the Earth, magnetism. It turns out that magnetism is nothing more than a part of electricity. What creates something to be a magnet or have magnetic properties is you have electric charges in the material, electrons, and those electrons spin. Okay, every electron has a spin. They all have the same spin, but the direction of the spin can change. So some electrons point up, some electrons point to the right, and so forth. So something is a magnet. Well, the first question is, well, if that's true, if all it takes is electrons spinning to create a magnet, then why isn't everything a magnet? Everything has electrons. There's not a single piece of material you know of that doesn't have electrons in it. Everything has electrons, including yourself. So if what creates a magnet is a spinning electron or a set of spinning electrons, then surely everything's magnetic. Well, no. There's one more thing that needs to be true. You must have these spinning electrons, but also they all must be aligned in the same direction. So if you have a set of electrons spinning in the same direction, now the thing is magnetic. Whereas something that's not magnetic, like a piece of wood, let's say, it's got electrons in it, and those electrons are spinning. The thing is, they spin in completely random directions. So they all kind of cancel each other out. So overall, you don't have this magnetic effect. But if you could somehow turn all of the electrons to all spin in the same directions, now you would have a piece of wood that's magnetic. So deep down, what we have found out is electricity and magnetism are actually part of the same thing. They're actually one thing, one concept. But they're broken into two pieces just because of our own kind of ignorance. We're used to thinking about them separately because magnets are different than charges. But fundamentally, they are part of the same phenomenon. So, and this is what's called electromagnetic induction. By induction, it means one thing causes another. You do this, you induce this other thing to happen. And so what happens is if you have, let's say, an electric charge and you move the electric charge creates an electric field around it. This electric field permeates all of the universe. Every single charge creates an electric field, and that electric field extends forever. When you move an electric charge, you change the field because it's moving location. So the starting point of the field is different. So obviously the field has changed a little bit. And it turns out that a changing electric field induces a magnetic field. So one way of seeing this is, let's say we have a wire. Here's a wire. And it's plugged into a machine. So let's say here's a wall with the power cord. And then here is the wire coming back on itself. And so this is like an outlet, and that causes electrons to flow. It causes a current to flow through the wire. Okay, so you have electricity flowing through this wire. If I put a compass underneath the wire, okay, what's going to happen is, well, the compass we know has a needle that's magnetic, and it points in the direction of north. So let's say north happens to be this way. That happens to be the north direction. So right now the needle should be pointing to the left. Well, because of the direction of this current, the current is a bunch of moving electrons. Moving electrons means changing electric fields. Electromagnetic induction says if you have a changing electric field, you create a magnetic field. That magnetic field affects this compass, and now all of a sudden the compass needle points this way. So here you have an object that's not magnetic, it's just a wire. It's just a wire with current flowing through. But it creates magnetism because it's moving electric fields, changing electric fields. And the same goes true the other way around. If you have a magnet and you move it around a coil of wire, you make the electrons move through the wire. You actually create electricity. This is how electric motors work. So by moving an electric field, you create a magnetic field. If you move a magnetic field, you create an electric field. That is what light is. Light is a wave of an electric field oscillating, waving around. As it moves through space, it's also producing a magnetic field, which is waving around. And of course, the fact that the magnetic field is waving around makes its electric field. And so you just have an electric field, magnetic field creating each other as it moves through space. And it looks something like this. I'm not very good drawing this, but say this is the electric field. And the electric field is just oscillating up and down. It's just a wave. And that wave moves to the right. So there's your electric field oscillation. The magnetic field oscillates because it's created by this moving electric field, but it turns out that the way it waves is always perpendicular to the electric field. So here the electric field happens to be up and down. So we'll say the magnetic field is back and forth. So it'll oscillate like this. You have to imagine it a little bit, but imagine this is the wave moving towards you and away from you. And that's the magnetic field, and that's the electric field. As the electric field moves up and down, as it propagates to the right, the magnetic field is moving in and out, in and out of the page or towards you and away from you. And that moving set of electric and magnetic fields is what is light. That is light. At least that's the wave property of the light. So now we know what light is. It's an electric field and a magnetic field inducing each other, propagating throughout space. This type of wave is what's called a transverse wave. Transverse refers to the fact that this wave, the waviness of it, is perpendicular to the motion of the wave, the direction of motion. So the wave is moving left to right, the oscillation is up and down. That's a transverse wave. So a water wave is a transverse wave. A wave on a string is a transverse wave. The other type is what's called a longitudinal wave. This is sound. Sound waves are longitudinal waves. And what that is the waviness is in the same direction as the motion. So if the wave, the sound wave, moves to the right, left to right, then the back and forth motion of the air molecules is also left to right. You're kind of pushing the air away from your mouth towards the person you're speaking. So you're pushing the molecules towards the person you're speaking, and they oscillate back and forth towards and away from that person. And the wave moves towards the person. That's what makes longitudinal waves. So those are the two types of waves. Transverse, the waviness is perpendicular to the direction of motion, the propagation. Longitudinal, the waviness is the same direction as the propagation. Light is a transverse wave. All right, so we have an image in our mind of what light is. And of course, there's going to be certain physical characteristics of the light. Number one, how bright it is. That's also called the intensity. Well, the bigger this wave is, the higher these peaks get, the brighter the wave. Or I could put it that way. Also, another thing we know about light is light has color, right? When we look around, we see some things are red, some are blue, some are yellow, some are white. They're all light. They're all the same substance, this electromagnetic wave, but something about it makes it different colors. That's what's called, or the way to see it in this picture is how quickly the wave oscillates. That is, how fast does it go up and down? It moves with a certain speed, left to right, so it travels with a certain speed, but the waviness, the oscillations, can be any speed. And so these characteristics we're going to study. The first thing to know, all waves have these characteristics. All waves. Now, we're, of course, going to be studying light, but as we study light, this is also going to include any kind of wave you can think of. So the first thing all waves have is a velocity. The velocity, of course, is how fast does the wave propagate through space. So when you speak, when you make a sound, the sound moves from your lips to the person's ears, and it moves with a certain speed. And anytime you make a sound, no matter what the sound is, all sounds have the same speed. Now, if you're not in air, let's say you go underwater. Well, now the sound moves at a different speed while it's underwater because the molecules that are waving are different molecules now. They're not air molecules, they're water molecules. Or if a sound tries to propagate through a piece of metal or a piece of glass or the wall, whatever. Different materials will have different speeds, but if you're in a material, let's say the air, then every wave has its own speed. Sound has a speed, 343 meters per second. And the same is true for light. Light has a certain speed. It's called, well, first of all, for all waves, the velocity is called v, obviously, just like in general physics 1. But if it's light, we call it c. This is for light only. We give it a very special variable because there's something very special about light that's not true of anything else. And in order to see it, you have to get into more and more physics. For now, just say that the fastest thing in the universe, there is nothing that moves faster, is light. And of course, that includes anything that doesn't have a mass. So gravity also would be treated the same way. Light has a very special speed because it's the fastest speed. And so we call it c. All other waves have their own velocity, less than c, whatever it is. And so we just call it velocity. The velocity of that wave is this, the velocity of that wave is this. It's not special. The velocity of light is special because it's the fastest speed and nothing can move faster. And in fact, nothing can even move that fast except for very rare things. And those things don't have mass. Things like gravity can also move at the speed of light. What is this speed? Of course, well, c is 3 times 10 to the 8th meters per second. Now, this is rounded, obviously. It's not like God, when he created the universe, happened to create light to move at exactly a nice round number of 3 times 10 to the 8th. You know, it's 2.98 or whatever times 10 to the 8th. But just like we rounded little g to 9.8 when there's more numbers after the 8, we're going to round the speed of light to 3 times 10 to the 8th. That's the number we're going to use. That's as fast as light goes in the air, in the vacuum. If it goes in water, it moves at a different speed. But whatever that speed is, it's always going that speed in the water. It never changes. And in air, it always goes this speed, never changes. So that's the velocity. Every wave has this thing called velocity because every wave moves. The next thing is what's called the frequency. The frequency, its variable is f, little f, and the units, of course, officially is 1/seconds, but that's a weird unit. So we redefine it, we give it a special name, which is capital H little z, which stands for hertz. Okay, that's the frequency. What is frequency? Frequency is literally, just as the name kind of implies, is how fast does the wave wave? How fast does it oscillate? That is to say, let's look at just the electric field. Forget about the magnetic field for now. The electric field is oscillating up and down, and we say, okay, in 1 second, how many times does it oscillate up and down? Let's say it oscillates 10 times a second. So it moves up and down 10 times a second. We say it's got a frequency of 10 hertz. If it oscillates 100 times per second, then it's 100 hertz. That's what the frequency is. So it's the number of oscillations per second. So that's the frequency. The last characteristic is what's called the wavelength. Wavelength is variable, is the Greek letter lambda, and it looks like that. That's lambda. And of course, the units of wavelength, it's a length, it's how long is this wave, and so it's in meters. How do we define it? Well, we think about the wave. We say, okay, look, this wave is propagating left to right So if I graph it, and this is position, this is the wave, let's say the amplitude, how high the wave is. The wavelength is literally how far does the wave travel when it does one oscillation. So this distance is called lambda. It is the distance traveled per oscillation. Okay. So obviously, the wavelength relates to these other two things. Because think about it. Let's say this wave oscillates 10 times per second. Okay, fine. Well, if the velocity of the wave is very slow, then it only moves a very small distance by the time it does one oscillation. But if the wave moves very quickly, it has moved a long ways before it does that oscillation. So velocity and frequency kind of combine together to give you a wavelength in some way. The wavelength depends on either how fast is a wave moving or how fast does a wave oscillate. So all three of these characteristics are related very strongly by a single equation. And that equation, the big equation, is the velocity of the wave is equal to the frequency times the wavelength. That's our big equation. This is the equation that relates the three big characteristics of a wave. If you know the frequency and the wavelength of the wave, you could get its velocity. Or if you know the velocity of the wave and its frequency, you could get the wavelength, and so on. Obviously, you know how to work with little equations. So that's the first thing we need to do, because you can get questions that say light has a frequency of 10,000 hertz. What is its wavelength? Well, in order to do it, you have to use this equation. So if you want the wavelength lambda, you need the frequency f and you need the velocity v. Well, I gave you the frequency, that's 10,000. I didn't tell you the velocity, but I told you it's light. And of course, we know light always moves with this speed. So you do know the speed, even though it didn't tell in the question, you know it already. It's the speed of light. So you'd use the two numbers, solve for lambda, and get your answer. Okay, so it's not a complicated equation. You don't have complicated questions, but it's an important one because it relates to three big characteristics of any wave, light included. Now, there are some other equations we need to know, or some other relationships. There's something called the period of a wave. The period of a wave, its letter, its variable is capital T, and its units are seconds. It's a time. And the period is literally the time it takes to make one oscillation. Time it takes to make one oscillation. So this sounds very close to frequency. Frequency is how many oscillations does it do in 1 second. The period is the time it takes to make one oscillation. They're kind of opposites. And indeed, the period is defined as 1 over the frequency. So if you ever need to know the frequency and you know the period or vice versa, you just use this equation, really easy. If you know the period, take the inverse, that gives you the frequency. If you know the frequency, take the inverse, that gives you the period. So that's another one that's helpful to know, the period of oscillation of a wave. It's just the inverse of the frequency. Now, the next thing, more theory about light, is there is an equation, a mathematical equation, or function, if you want to call it that, which describes a wave. And it describes a wave in such a way as you can predict what will the wave be like at some other time or some other location. And so we want to know this. This is very helpful. If you can define a system by a single equation, then you can make lots of predictions. That's the point of being a physicist. And so it turns out that the big equation for any wave, not just light waves, but it works for light as well, goes like this. We'll call it the equation of a wave. The equation of a wave says y as a function of x and t. Fancy mathematical terminology. All this means is the number y I'm about to get, the answer, is a number. And that number depends on x, the position, where am I going to test, and t, at what time am I looking for the answer. So pretend you have the system something like this. We have we're in, I don't know, Orange Beach. And so we're looking out at the Gulf of Mexico and we see the waves crashing onto the beach. And I say, okay, I can write down an equation which defines the waves in the Gulf of Mexico. And so what you can do is you can predict, okay, if I'm sitting here on the beach and I'm looking at this position over here in the water. So you're looking at a particular X, a particular distance. You say, when I look there, how high will the wave be in 10 seconds? Okay, that's a prediction. That's a question you can ask. Just like if you have something like you're standing on the top of a 10-meter high cliff and you drop a rock. How high will the rock be after 1.5 seconds? Okay, we do that in first semester physics. Here we have a wave. We know the equation of the wave, let's say. And so you can say, how high will the wave be at this location at this time when I look? That's what this says. So y, the height of the wave at a particular point in space at a particular time, which you would tell it, is given by, let's call it A. A is a number, and this is called the maximum amplitude. And all this number is what is the highest the wave can possibly get. So we know the wave will never get bigger than this number. This is the biggest the wave will ever be. That's the number I put here. So maximum amplitude, the biggest the wave can get, times the sine of, now this is where it gets slightly messy. It is 2 pi over lambda times x minus 2 pi f times t. There's our equation. So in order to use it, what would you need to know? Well, you'd have to know lambda, you'd have to know A, you'd have to know F. So if you knew the frequency of these waves, you knew the wavelength of the waves, and you knew the maximum amplitude of the wave, you'd feed those numbers in, and then you'd say, okay, at a position X, let's say 5 meters away, and at a time 10 seconds from now, how high will the wave be? I plug all those numbers in, and I get a number, 1.5 meters or something. That's how high the wave will be. If I look at 15 seconds, what will the height of the wave be? Maybe 0.8 meters, whatever. That's the big equation. And any wave is defined by this equation, which is very nice. Now, of course, it's a bit messy. What is up with these frickin' 2 pi's everywhere? So what physicists did and mathematicians is they said, look, I don't feel like writing 2 pi f every single time, or 2 pi over lambda. That's ridiculous. So they do what they always do. They make the equation look pretty, by creating a new variable. And so what we did was we have omega, which is a Greek letter omega. It looks like kind of a curly W. Omega is called the angular frequency. And omega is literally 2 pi f. So they took 2 pi f and they said, instead of writing 2 pi f, I'm going to write this symbol instead, omega. The units are not hertz anymore, they're radians per second. Because now it's angular frequency, it's not regular frequency. Regular frequency is hertz, angular frequency is radians per second. Then they made another variable, k. This is called the wave number. What is the wave number? Obviously, if you look at the equation, it's very easy to see. It's 2 pi over lambda. And so by making these substitutions, by creating these new symbols, now our equation looks a lot prettier. Y is a sine kx minus omega t. Much easier to remember. You don't have all those stupid 2 pi's all over the place. It just looks nicer. It's the same thing. It's just that written like this, it's easier. It's easier on the eyes. And so all you have to do is every time you want to plug in omega, you just plug in 2 pi f, some number. Put it in your calculator, you get a number, that's omega. And k is this thing. Plug that in your calculator, you get a number for k, you plug it in. So that's the equation of a wave. And so with this, we can answer questions. Like I said, there's a light wave moving along with a wavelength of this and that, and a frequency of this, whose maximum amplitude is whatever. Tell me what will be the height of this wave at this location at this time. So you plug in the wavelength and the frequency, maximum amplitude. And then that's when you're free to play with your x and t. You say, okay, this position, x, this time, t. Plug all that stuff in your calculator. It's just a sine wave, sine function, and you'll get a number. That's the height of the wave. Or if this is water waves or sound waves or whatever. So this is all the theory about light. This is a theory about light that we're going to be talking about or doing questions on. First big thing, the characteristics. Velocity is frequency times wavelength. Period is in there as well, not quite as important, but you need to know period and frequency are inverses because sometimes you'll see the term period of a wave. And then the equation of a wave. You could learn either one. I learned the bottom one, and I just know k and omega as well, because the bottom one's easier to write. Kx minus omega t is in my brain. Or you can learn the top one if you don't mind having the 2 pi's in your equation everywhere. So those are the big equations we need to know for this theoretical part of light. Are there any questions about what we discussed so far today? Well, I know this has been kind of dry. It's purely the theory stuff. I wanted to get it all out there. There's a lot of really interesting stuff when it comes to light. I mean, obviously, special relativity, one of the most interesting and fascinating concepts in all of physics, just because of the fact that it's actually real. For instance, here's a concept that's kind of strange. If you're on a car, or let's say you're on a train, it's always a train. Here's a train. And you're up on this train like this, and the train's not moving, and you're holding a ball, and someone over here is watching you. Okay? So here's my train. This isn't moving. You throw the ball. You can throw the ball with a velocity of 10 meters per second. So you say, what does the person see? Person sees a ball moving at them with a velocity of 10 meters per second, obviously. But then if instead we allow the train to move with a velocity of 30 as well, now the question is, what does the person see? Well, the person would see before you threw the ball is moving at 30 meters per second already because it's on the train and the train's moving at 30. Then you throw the ball, giving it an extra 10 meters per second. So this person would see the velocity of the ball be 40 meters per second, whereas before it was only 10. Because the source, the ball, is moving towards you before it's thrown. So the source of this object, its motion affects the speed you're going to see. This is what's called Galilean transformation. Galilean after Galileo, obviously. And it says that in order to find the velocity of an object, you need to know the true velocity of the object by itself. And then you add to it or subtract, depending on the motion, the speed of the source or the measurer. If you're running towards the person throwing the ball, then to you, the ball seems to be moving faster than if you weren't running towards it at all. Of course. Now with light, this doesn't happen. If instead of this being a ball, this was a flashlight or a laser pointer, and instead of the train moving at 30 meters per second, it's moving at 80% the speed of light, and this person measures how fast the light comes towards him, he would say the light comes towards him at 3 times 10 to the 8th before the train moves. And then when the train starts to move, well, now you'd say, okay, well, if it wasn't moving, the light comes at 3 times 10 to the 8th. Now it is moving. I should add the speed of the train to the speed of the light, because the light was already moving because of the train, and now it's moving faster because it got sent off. But no, when the train moves, the person still sees the speed of light as only 3 times 10 to the 8th. And no matter what you do, no matter how you move, no matter how the source of the light moves, no matter what, you will always measure it at 3 times 10 to the 8th. So another way of saying it is, you and a friend have your stopwatch and your rulers out, and you're going to measure the speed of light coming towards you. You're standing still. Your friend is running towards the person with a flashlight. At the end of the day, you get back with your measurements and you have exactly the same speed. The fact that he was moving towards the light doesn't make the light seem faster. Light is the only thing this is true for. If this were tennis balls, if this were sound waves, if this were anything else, anything in the universe, you would have to add the velocities. Light, you don't. Which means something very weird. What it means is that when you move towards the light, everything else changes. Time changes for you. Your stopwatch ticks slower than it would have if you were just standing still. And your ruler changes size. It gets shorter as you run towards the light. Physically, literally gets smaller. The light literally, the time literally slows down. And it's not just some weird, we say, pretend like the lights or time is slowing down. No. Literally, if you're on a rocket ship, and so you're on a rocket ship, you leave Earth, and the rocket ship is moving really close to the speed of light. You're moving very, very fast. You live 5 years of your life on this rocket ship. You come back to Earth. You've lived 5 years, literally 5 years. Your biology says it's been 5 years. Everything about you is 5 years older. Everybody else on Earth is 400 years older. Because time for you was different than time for the people that were not moving. It is a literal change of time and space when we start getting into these effects. When we start going near the speed of light, physical things change. And so people will live longer. The satellites going around the Earth, the GPS satellites, they have to take into account that the clock on the satellite ticks slower than a normal clock on Earth would. Because if it didn't, then all the distances and all the measurements of the GPS would be off. So they literally have to do these mathematical calculations in the satellite to say, yeah, the satellite says it's only been 2 minutes, but it's really been 2 minutes and 0.0001 second. There's extra time that has passed that the satellite doesn't know about. So there's very fascinating concepts that we just can't get into because number one, we don't have the time, but number two, they're a little more complex than we can get into for our knowledge base now, both mathematically and physically. But know that this stuff exists. It's not fake. It's not just, well, we say it's like this just to explain it, but it's not really. No, time literally does slow down. And so if you had a twin and the twin went on a rocket ship, you'll live the rest of your life, 100 years, let's say, and your twin will come back and he'll only be 20 or some other age, depending on how fast he was moving. And it's not like, oh, well, yeah, but then by the time he gets back to Earth, everything settles out and he starts to age more quickly. No, he ages normally. And to him, he had no idea. He was just living his life. He doesn't feel slower, doesn't feel like time is any different. It feels normal. You can't tell that it's happening. It just does happen. So really, really interesting effects. For now, we have to deal with the slightly more mundane stuff, these equations. But that's just to set up for what comes in the future. Now, the plan is next time, I said this at the beginning, not everybody was here at the time. The plan for the rest of the semester is we've got today, which we did. We've got next week, Tuesday and Thursday. And then the following week, Tuesday, is the last day of class before finals. So we're going to do optics for today and next week. We will not have a test on optics, but optics will be on the final exam. And so that Tuesday, our last day of class Tuesday, will be our final exam review. Okay, I figured this is the best way to get a little bit of this topic in, since you'll be seeing it when you get to general physics, with the little time we have left. I won't be able to get through all the topic. I won't be able to get to lenses and stuff like that, but I can get to some stuff that's important. So you can see it now. That way, when we get to it in general physics, you'll be kind of used to it. So next class, I'll do a few examples working with these equations. So you see how to work the equations. And then we'll move on to the next piece, which is called polarization. There's another characteristic of light I did not discuss, which is called polarization. It's important because things like 3D movies make use of polarization of light. Now, it's not something our eyes can see. We can't look and say, oh, this light is polarized this way. Our eyes can't detect it, but cameras can detect it, or film or lenses or things like that can detect polarization. And so we want to talk about it. That's what we'll do next time. And then I think we'll get into refraction, which is the bending of light. And that'll probably be the last topic we'll get to for the semester. So unless you have any questions, that's all I have for you today. You are free to go and enjoy the rest of your day. I will see you on Tuesday.